So in this how-to video, we are going to look at Lewis dot structures, and specifically Lewis dot structures of covalent compounds or molecular compounds. Compounds that contain elements from the upper right-hand portion of the periodic table are nonmetals. So looking at this, covalent compounds and ionic compounds differ primarily because covalent compounds share electrons, whereas ionic compounds give or take electrons. So we kind of need to focus on how many electrons atoms need to be stable, and that is 8, which is the same idea we were looking at when we were trying to draw ionic compounds and balance those out. But in this situation, the 8 electrons don't necessarily stay with one atom or one compound or one ion at a time. In this one, the atoms will share them. We also need to recognize that hydrogen and helium only need 2. In terms of protons and electrons, when we're looking at something like a polyatomic ion like this, for it to have -2 charge overall, there's an extra 2 electrons that are hanging out here. So we're going to look at our periodic table, and we're going to identify how many electrons some of these have. So phosphorus is hanging out underneath nitrogen, and so it is in the 1, 2, 3, 4, 5, the 5th column over, ignoring the metals at the short stack of metals. So this one has 5 valence electrons. Oxygen is one row over, so it has 6. Carbon is one row back from phosphorus, so it has 4. Hydrogen only has 1 valence electron, and chlorine has 7 valence electrons. Let's kind of go through these rules for drawing Lewis dot structures based off of doing an example. So first we need to count the number of valence electrons for each atom in the molecule. So we have carbon, who has 4, and we have hydrogen, who has 1, but we have 4 of them, so we're going to multiply by 4 and get 4. So overall, we have a total of 8 valence electrons. Next, we're going to draw kind of a skeleton of the molecule. For the most part, anything that is listed as just having one of something is kind of our central atom. So in this case, we're going to put C in the middle, and then we are going to join it to the other atoms, the 4 hydrogens, with single bonds, and those are just drawn with lines. And each of those lines represent 2 atoms. So we have, for carbon, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Well, we only have 8 valence electrons total. Carbon has the 8 that it wants. Each of the hydrogens have the 2 that they want, so this guy is good to go. Now we know that some covalent compounds or some molecular compounds can have slightly charged sides to it. And it's important to look at the structure that we've drawn to identify if we have charge or not. And really, the charge comes from having some electrons that are hanging off by themselves, or that uneven sharing of electrons throughout the entire thing. So for example, in letter A, we have pretty much no matter which way you flip this around, it's going to look the exact same way. So we say that it is symmetrical. Since it's symmetrical, it doesn't have any areas where there's extra electrons or extra negative charge, so this would be non-polar. Next, let's take a look at water. So we start from the beginning with our steps, and we count the number of valence electrons for each atom. So we have H, which has 1, but we have 2 of those, so we're going to multiply by 2 and have 2 total for hydrogen. Oxygen has 6, so if we add these together, we get 8 total valence electrons. Step 3, we need to draw a skeleton. So we're going to start with oxygen in the middle, and we're going to attach hydrogen to each side. Now, we need to place lone pairs, this is step 4, place lone pairs or dots around the molecule to satisfy the octet rule. We have 1, 2, 3, 4. So this hydrogen over here is happy, and this hydrogen here is happy because they only want 2 and they have 2. But oxygen only has 4. So we add lone pairs around the oxygen so that way we satisfy the octet rule. And now oxygen has 8 electrons that hang out with this. We're going to count the total here and see if it compares. Well, we have 1, 2, 3, 4, 5, 6, 7, 8. And we have 8 valence electrons total, so this works out. There's one more scenario that we might come into play, and that is in letter L, CO2. So I've already got my tallied numbers that we had 4 for carbon, and we had 12 coming from the oxygen that totaled 16. So I have here, I've drawn my molecule with my 1 bond apiece, and now I need to go in and fill in my electrons to make sure that everybody has 8 like they would like. So here is everything with their 8 valence electrons, or 8 electrons hanging out on each one, and we need to count these. And if we count them, we will notice that we have 20 electrons, and we're only supposed to have 16. So this is a problem. And what we find is that maybe carbon and oxygen don't just share these 2 electrons here, but maybe they share another set. So if we took this pair of electrons and put it here as another bond, carbon wouldn't need these electrons up here because they would have the sharing of these 2, the sharing of these 2 down here, and these 2 here. In doing that, we reduce this number of 20 down to 18. Now that still doesn't solve our problem, but it gets us a little closer. We can also do that on the other side. If we take these 2 electrons and make them into a bond, then carbon wouldn't need these down here because it would have the 4 electrons it was sharing on this side and 4 electrons it was sharing on this side, and carbon would be happy with the bonded electrons. Oxygen would still be happy because it's still using its own. So we would be able to reduce this number to 16. The resulting compound would really look like this, where we have 1, 2, 3, 4, 5, 6, 7, 8 on the oxygen. Carbon would have 1, 2, 3, 4, 5, 6, 7, 8. So it's happy, and the oxygen on the right would have 1, 2, 3, 4, 5, 6, 7, 8 atoms as well. Total, we have 4 from this oxygen, 4 here, that's 8, 4 here, that's 12, and 4 here, that's 16. So we've matched our 16 valence electrons that we've had because we've made these double bonds. To just take this a step further, we can look at if this is symmetrical or not, and we can say that it's asymmetrical because if you turn this 90 degrees, it's different. Plus we have these extra little electron pairs that are kind of floating around. That makes this a polar compound.